Welcome to PowerUp, a podcast show hosted by Maurizio Di Paolo Emilio that brings life to some of the stories on power electronics technologies and products featured on PowerElectronicsNews.com and through other AspenCore media publications. In this show, you'll hear both engineers and executives discuss news, challenges and opportunities for power electronics in markets such as automotive, industrial and consumer. Here is your host, Editor-in-Chief of PowerElectronicsNews.com and eeweb.com, Maurizio Di Paolo Emilio.
Hello everyone and welcome to this new episode of PowerUp. Today we'll talk about wide-bandgap technological advancements in terms of gallium nitride and silicon carbide. Wide-bandgap materials such as silicon carbide, SiC or SiC and gallium nitride or GaN enable significant efficiency improvements in applications such as traction inverter for SiC, adapter chargers, for example for GaN. Silicon carbide and gallium nitride technologies have grown enormously over the past few years, proving to be commercially available energy-saving technologies. These wide-bandgap semiconductors complement each other to address a wide range of applications in which energy efficiency is important. Today in this podcast with Sebastian Fahlbusch, Manager Power Product Application Competence Center at Nexperia, and Dilder Chowdhury, Director Strategic Marketing Power GaN Technology at Nexperia, we dive into technological advancements such as silicon carbide MOSFET and GaN FETs. We would like to understand the strategic collaboration about Nexperia and Mitsubishi. And moreover, we will analyze the Nexperia commitment to sustainability and its vision about in terms of application market for silicon carbide and gallium nitride. Let's talk with Sebastian and Dilder. Hi Dilder, hi Sebastian. Thanks a lot for coming on at PowerUp Podcast. How is it going?
I'm fine, thank you, Maurizio. Thanks for inviting us.
Thank you, Maurizio. Nice to meet you again.
Where are you located, Sebastian?
I'm located in Hamburg, Germany.
And you, Dilder?
I'm located in Manchester, in the UK.
Good. So today we will talk wide-bandgap advancements in terms of silicon carbide and gallium nitride. Before that, so tell us more about your background. So introduce yourself and give us a little bit of your background information. Let's start with Sebastian and then Dilder.
Yeah, okay, no problem. Yeah, my name is Sebastian Fahlbusch. I'm manager of a team of product application engineers for silicon carbide at Nexperia. In that role, we support the company with application insights, and it comprises the support of the development process, so from the very early beginning of the products up to the customer support activities. In that sense, we act as some kind of interface.
Thank you, Sebastian. Dilder.
Yeah, my name is Dilder Chowdhury, and I'm based in Manchester in the Power Division headquarters for Power GaN Technology. And I'm the Director of Strategic Marketing. And following my PhD, I joined the Philips Semiconductor, NXP, and eventually Nexperia. And was working with the Power GaN Technology from the inset of this department. And I was a GaN architect and also international product marketing manager, now the Director of Strategic Marketing. Thank you.
Thank you, guys. So let me share the first question about silicon carbide. So the introduction of Nexperia's 1200 silicon carbide MOSFETs has the goal to address various applications in industrial application industry. So Sebastian, could you elaborate on how these MOSFETs would take the leadership of electric vehicle applications, but not only, also UPS, solar inverters, and so on?
Oh, yes, of course. Well, generally, the applications that you mentioned, they of course benefit from silicon carbide's superior conduction and switching performance, especially in the 1200 volt domain compared to other available power semiconductor solutions in 1200 volts. Well, I think a lot of times we already spoke about silicon carbide's benefits in general. I think it's widely discussed. So let me focus a little bit more on Nexperia's specific benefits when we compare them versus other silicon carbide MOSFETs solutions that are available in the market.
Sure.
And here the answer, in my opinion, is quite simple. Nexperia's SiC MOSFETs possess worldwide one of the, if not the highest RDS(on) temperature stability. What does that actually mean? It means that no other device will maintain such a low RDS(on) compared to the initial 25 degrees Celsius rated RDS(on) when the junction temperature changes during operation. Maurizio, let me give you an example. For example,
Sure.
if we look at 40 milliohm devices, which we have already released, and they're rated at 25 degrees Celsius junction temperature. This device rises up during operation when we hit 175 degrees Celsius junction temperature to only up to 54 milliohm RDS(on). So the rise is in the range of, let's say, a factor of 1.4. When we compare that with other vendors, there were a lot of other vendors in the market. When they also start with 40 milliohm, they end up sometimes beyond 60, beyond 70, even beyond 80 milliohms. Sometimes I saw already 88 milliohms at 175 degrees Celsius. So that's really a big difference in performance, as the RDS(on) dictates at a given operator condition the conduction loss. The question is now, where does this stability help in application? As I said, RDS(on) dictates more or less the conduction loss part in any kind of application, and especially when the load condition in a converter is high. So let's say high power operation in the converter. This can happen. You asked for specific applications. This can happen, for example, when the charger is operating in this constant current mode where the maximum charging power happens, or in solar applications, for example, when you have full sun exposure situations, so more or less maximum power out of the solar panels. That's the moment where these kind of applications have to convert the maximum energy at highest current, and that's where the conduction loss massively comes into play. You can imagine, if other devices go higher in RDS(on) than ours, we have a benefit there at the same current conditions in conduction loss. And the beauty of this is it's actually regardless of the application, regardless of how the devices are switched. They can be switched hard switching topologies, soft switching topologies. RDS(on) stability leads naturally to an advantage in conduction loss over the whole converter range. And in that sense, temperature stability is more or less a very universal advantage of our solution. And it can lead to energy savings, especially under this high power conditions when the device massively heats up. If you have an advantage there in efficiency, so that you have to dissipate less energy compared to other solutions, this can give the hardware designers a degree of freedom to also shrink the heatsink. So which is, in that sense, also a possibility to reduce cost, as heatsinks obviously are also a big portion of the overall system cost. And maybe let me add just one last thing to it. What I noticed is that from many customer discussions I had is that this is an often overseen benefit, simply because, when hardware designers start to pre-select their potential SiC MOSFETs candidates, they start to compare them first by 25 degrees Celsius. And they assume, that's at least what I guess, they assume that more or less this temperature stability is more or less harmonized among the group of all the technologies. But actually the opposite is true. So that can lead to the situation that if you want to have under high temperature situation, the same conduction loss performance, customers need to be aware that they actually have to compare sometimes even a little bit asymmetrical. Sometimes, for example, 40 milliohm of our device compared to maybe 25 or 30 milliamp of another to get the same RDS on at elevated temperature.
Yeah, thank you. So, as I mentioned at the beginning, Nexperia announced time ago a collaboration, strategic partnership with Mitsubishi. Maybe you can, in terms of silicon carbide, maybe you can elaborate a little bit this partnership. What benefits can this collaboration bring to the industry?
Oh, yes, of course. I'm happy to do so. Regarding the partnership with Mitsubishi, it's actually something we call a long-term co-development partnership with them, which intends to leverage the technology expertise of both companies. I mean, ultimately, we want to provide to the market innovative power semiconductor solutions for a broad scale of applications. By the way, that's the reason we have this RDS on feature. And that with more or less mass market suitable solutions of highest quality, and that together with technical innovation. This is more or less part of both company's DNA. That's the reason for us. Mitsubishi was an easy choice for us to work with, a logical decision to combine our strength with clear mutual benefits.
Thank you, Sebastian. So in terms of wide-bandgap Dilder, let's talk about GaN. So Nexperia has introduced GaN FET devices for several applications, industrial renewable energy application. So how does this technology enhance energy efficiency? What advantages, in particular the proprietary copper clip CCPAK surface mount packaging would offer? But also Nexperia released time ago E-mode, enhancement mode configuration for low voltage and high voltage. Maybe you can elaborate a little bit about low and high in this case. So Nexperia now offer designers a selection of GaN FETs, Cascode, E-mode. So how do you manage the portfolio for specific applications?
Yeah, my favorite question, because as you know, fundamentally I'm a physicist. And obviously the whole journey of gallium nitride started from what is called HEMT. Instead of normal transistor, it's called HEMT. That was a high electron mobility transistor. And that mobility is related to the electrons that make the conduction and the transport phenomena. What it means that this high electron mobility is not compromised even at high temperature or elevated temperature. This is one of the advantages of the GaN. So what it means is during switching, not only that it travels fast, it also doesn't slag. It doesn't slow down at high temperature. This is one advantage. Another, because it's a very high bandwidth material, and a high critical electric field material. What it means that the electron actually need to travel a smaller distance. So you have got two advantages. It's a faster. If you've got a pause, if you've got a faster, then you'll have to only travel about 1/3 of the distance or half of the distance or even 1/10 of the distance, which means that these devices are really, really fast. So to take the advantage, you know that there are two configurations. One is the E-mode, which is the which actually disrupts the naturally occurring two-dimensional electron gas, which is that is formed between GaN and L-GaN interface. And during conduction, obviously, it forms the channel and makes the conduction. On the other hand, the Cascode makes the conduction naturally because we do not disrupt it. We only disrupt it to turn it off. So it has got a much better conduction path compared to the E-mode. What it means is that E-mode has got some process limitation where aluminum concentration within the E-mode devices is significantly reduced compared to the Cascode devices. What it means for the higher power applications, high voltage, higher power application, we position our cascode devices. On the other hand, lower power, high voltage, and the lower and higher power, low voltage, we position our E-mode devices. So we do not consider these two technology competing each other. We consider them to be perfectly matched complementary positioning to cover all four quadrants. Yeah. So this is the advantage, and our portfolio actually reflects that one. You will see that all the higher RDS-on products in the high voltage is actually E-mode, and the lower RDS-on products coming out of the cascode. And it is fundamental that if you have got a very good semiconductor, you need to have a very good package to complement to take the full performance into the application. That's the reason our innovation of the cascode, the CCPAK or the all copper clip package comes into play. So because we have got the automotive mindset, we care about the performance, we care about the board level and reliability of the products as well. So all these actually combine and reflected in our cascode solution in our copper clip package, because this has got a low inductance, high reliability, and it also gives the high performance and highest board level reliability as well. On the other hand, on the E-mode, we position it for the low voltage and the high voltage low power, where they will give you a low inductance again, because most of our package offering on the E-mode is like a QFN package, which has got a naturally low inductance, and also the chip scale packaging, that also gives the low inductance. So that's how we position our portfolio, and obviously right up to 650 volt, starting from 40 volt in our portfolio. I hope that clarifies our portfolio positioning.
Thank you, Dilder. So, and in terms of packaging, so let's talk more about this one for, as you mentioned, for GaN cascode. So, so if you could explain how the CCPAK technology packaging in GaN cascode switches would represent a breakthrough in semiconductor. So let's analyze a little bit better in terms of benefits that this packaging approach can offer.
Absolutely. So obviously, you know that the CCPAK, no one has ever brought this package in the market. We are the first one, as we've been the pioneer for our LF pack as well. So we have got about over 20 years of experience of the benefit of the LF pack, and that's we have translated into this high voltage gallium nitride. So we looked into the gallium nitride properties and the performance of the die, and says how we can maximize the performance to get to the outside world. So we need a package that can translate that one appropriately. So the copper clip package actually innovated towards that direction. So if we have got a low inductance package, which is achieved through the all copper clip. So we do not have any wire bonding in the package. And because the cascode, we need these low voltage silicon devices to sit very close to the high voltage GaN devices. And to avoid any mid-node inductance, basically we physically put the low voltage silicon FET on top of the GaN FET so that there is no mid-node inductance. Even though these two devices are manufactured in two different fab, but because of the positioning of one top of another, it's almost like a single fabrication technology. Then we put all copper clip in the source, in the drain, and also in the gate. Along with the gate Kelvin, we also put using copper clip. So all these, what it does, not only that it helps in the thermal transition, because of the copper clips actually takes the heat away, it also gives the lowest possible inductance that we can think of. And the gull wing packaging legs that comes out are actually shock absorber. Not only is now we have got a package that has got the robust inside, low inductance inside and through the package, and also it has got the advantage of the gull wing so that it can absorb the shock in the PCB board. As the PCB board has got multiple components, and also mechanically it is actually stretched quite a bit. And so because of those movement and these gluing packaging legs actually compensate for any movement. And so we have done over, say, 30,000 cycles in the thermal cycle, thermal shocks, and show that they compared to like QFN packages, this package actually goes about double, triple, quadruple times. It still sustain the reliability. So that's the story.
Yeah, it's a big advantage in terms of reliability, of course.
Absolutely. Along with the performance.
Yeah. So, just in conclusion, come back to Sebastian, and then for Dilder, the last one question. We mentioned a lot of application in terms of silicon carbide, and talking of, again, of course, packaging and related applications. So how versatile are these new semiconductor technology? What potential future do you foresee for SiC, SiC or SiC silicon carbide, and again, devices with regard in terms of sustainability? And also you can mention some updates, what's next from Nexperia in terms of silicon carbide, and then Dilder for again. Sebastian.
Okay. Let me start with how versatile our technology is and what comes next. As I already said, in terms of the temperature stability, which is so advantageous for so many applications, since it addresses, if not the main contributor of losses in power semiconductors, namely the conduction losses. From this side, we can say if it can especially be beneficial there. Our solution obviously is highly versatile because it's beneficial in one of the main contributors. And not to forget, when we look from the other side, when we look also how the device is driven, we can drive the device with absolute standard drive voltages, which makes it also drop-in replaceable to other silicon carbide vendors. So it should be easy for a lot of our customers to incorporate our technology and see immediately the benefits, as I mentioned before, in the high power loss, high output power converter range. In terms of the future applications, I think SiC's success story will go on, obviously, in the automotive segment, which is clearly forecasted, and we have almost with all car OEMs and tier ones discussions about it. And it's already, as you know, silicon carbide is already in automotive application and EVs. So it will be definitely be driven by the electrification of cars. I think that's for sure. But going a little bit beyond that, I personally expect that this 1200 volt silicon carbide market will expand even more, for example, to the motor drive applications, especially with the increasing energy prices, drives with emission profile which has to operate a long time or even permanent, like in some air conditioning or conveyor belts or stuff like that. So where something rotates the whole day, these loss savings from silicon carbide can be more or less immediately be used, and it's visible for the customers. And especially when we look at the customers, how it changed, they are more and more aware of total cost of ownership, energy labels, etc. So this is really something that drives silicon carbide. And even beyond that, what I personally expect is also that the heat pump market gives silicon carbide now a chance to also make really, especially 1200 volt, give the possibility to also get into households, for example. And maybe just one last one. What I also have seen a lot of discussions ongoing is the classical solid state circuit breakers. There also silicon carbide seems to be a very interesting solution. Really interested and curious how this will proceed.
Thank you, Sebastian. Indeed, I'm going to post an article about solid-state circuit breakers with silicon carbide. Dilder.
Of course. It's complementing my previous answers. The sustainability question is actually quite fundamental question now for every industry. And the reduced carbon dioxide footprint is another. Not only that it is discussed among the people, it's actually coming out of the legislation, the government rules and regulations, why there is a huge enhancement of the electrification everywhere. Electrification of car, electrification, everything that we mechanically move, including even our white goods. Even though we originally thought white goods doesn't need a solution because they have got so much space, why do you bother, right? Now they are coming back because now they can reduce their solution size. So, and harmful emission to the world. And all these down to the low efficiency of the power conversion. And this is the heart of the matter. Lowest efficiency in the power conversion. Power conversion is dictated by the switching and the conduction losses. And this is where the gallium nitride and the silicon carbide comes in. And obviously, in this journey, the highest possible efficiency you can achieve through gallium nitride. Moving from 90% to, say, 99% is almost like 10 kilowatt. If you have got a 100 kilowatt system, 10 kilowatt versus 1 kilowatt. So it's a huge, and all losses are, we know that it's losses as heat, and which is not good. And then you'll have to cool it down, and it makes lots of space and the heat sinking. And the highest power density. Now that you can achieve it from a smaller packaging, and the gallium nitride is also very fast. That's why you can actually increase the frequency, reduce your passives like your capacitance and also your inductance. Your solution size gets smaller and smaller and lighter. So the applications, we know that the consumer applications are already accepted gallium nitride solution. And there are many adapters and small power conversions are there. And there are obviously then SMPS and the power supply market where we see that there is a penetration and moving from 1.5 kilowatt to 1.6 kilowatt with a reduced cost and reduced size. And it goes, as it goes into the industrial application. Heat pump is another application where gallium nitride can go in. The UPS, the solar inverter, server storage, you know that they says that we pay twice for our large server farms. Because one is we buy the electricity from the grid, and because it is so inefficient, we need to cool it, so we buy again electricity to cool it down because of the inefficiency. So this is where the gallium nitride can help quite significantly. Then telecom infrastructure and all those areas, and obviously industrial, motor control, and automotive application, eventually it will penetrate into to help for a lighter and more efficient solution on the onboard charger, DC-DC converter, and eventually there will be a coexistence of the silicon carbide and the gallium nitride in the traction inverter. So basically anything that is switching, you have got the gallium nitride need to be there. So it is in a broad sense, that's how it. You know that the Class D amplifier also achieves significantly better fidelity as well using gallium nitride solution. So stories goes on. So I hope that covers.
Thank you. Good. So efficiency is important, and it's time for wide-bandgap, GaN and silicon carbide, so they can solve each issue in terms of power conversion to increase, as Dilder said. So guys, thanks a lot for being part at the PowerUP podcast. Thanks a lot for joining us. Thank you, Sebastian. Thank you, Dilder. And see you next.
Thank you very much, Maurizio.
Thank you, Maurizio. And thank you really that you established this podcast. Really exciting. Thanks.
That brings us to the end of this episode. Stay tuned with more news and technical aspects about power electronics. If you are listening to this on the podcast page at eetimes.com or powerelectronicsnews.com, links to articles on topics we have discussed are shown on this page. PowerUp is brought to you by Aspen Core Media. The host is Maurizio Di Paolo Emilio, and the producer is James Eade.